So this is probably going to be the last talk of the conference. I'm going to present my projects that are called Tangle and Mangle, and I'm going to explain how I'm doing threaded OpenGL dispatch. So the plan of the talk is to explain the overall concept, show some implementation details, show how I'm trying to make it fast, and then even some more, and touch upon some features that look like they should be in OpenGL, but surprisingly are not. So when an application makes OpenGL calls, imagine you get the function name, you store the function name and the pointers into a buffer, and then you can use that buffer to actually execute the function with those arguments, and that's how, for example, API trace works. And surely you can do the same as well in the same process. And what you do is you store the arguments into a buffer, and you do not call the actual OpenGL function, but you have a secondary thread that will call into the driver with those arguments and have the driver do the work. So as long as you can postpone the work in such manner, you can hope to have some performance improvements from getting the driver overhead away from the application thread somewhere else. But surely you cannot do that all the time. For example, if the API call returns a value, you cannot fake a value, not easily at least. If the call is going to access application memory, then you have to be careful as well, because after the call, the application may want to inspect that memory, or that memory can be gone because it can just unmap it. Some functions are specified to be synchronous, for example, shell finish, and some functions you just want to keep synchronous because you do not want to increase the latency. For example, applications can reasonably expect that GLX swap buffers has some reasonable relation to the actual swap buffer event, and you do not want to increase the latency because then the gamers will hate you. So what you can do is either you can synchronize, so you just catch, you wait until the secondary thread catches up, and then you guarantee that everything has happened in the correct order. Sometimes you can just copy a small array if that is all that needs to happen. And in some other ways, you can just use how the certain function is specified to work. More on that later. Surely it will not work all the time. For example, if the application is totally GPU bound, you are not affecting the bottleneck, the GPU will not go faster. If the application is CPU bound and the driver is not on the critical path, you are not doing anything to help that. So ideally what needs to happen is that the application is structured in such a way that OpenGL driver lives in its critical path, and there is enough work that can be overlapped with OpenGL calls that you move away from the application thread to a secondary thread. So certainly this work is nothing new. It has been done. NVIDIA did a Linux implementation that is activated by an environment variable called child thread optimizations, and that was a few years after a similar implementation was appeared in the Windows driver. In Mesa, there is a merge branch that was worked on Eric Angelte and Paul Berry. And what I'm going to do differently is to make it a standalone implementation, so it is not bound to Mesa, but can be used with the NVIDIA driver as well. And it will come with a profiler of sorts to show why the great optimization doesn't help so when you apply it to a certain game, why doesn't your FPS rise? And I think it comes with a some interesting other concepts as well, or hopefully. So what I'm going to explain in the next slides is how the implementation is structured. So it needs at least one secondary thread to actually perform the OpenGL work, some mechanism to pass function IDs and arguments to that thread, a way to synchronize when you need to wait for it to catch up and so on, and how the actual OpenGL calls are being made. So to make the threaded afloat, we need the worker thread, and the model that I'm using is to have one worker thread for each application thread that happened to do something with GL or GLX. So this is a one-to-one correspondence. It is crucial not to touch libgl from any of the original application threads, because, for example, there is no easy way to have a good ordering between what you're doing in the original thread and what is going to happen synchronously in a secondary thread. And so when an application thread makes a GLX call, you check if a worker has been spawned for this application thread. If not, you create it. If an application makes a GL call, either it has made a GLX make current before and you have a worker, or it invokes undefined behavior and, well, who cares? And surprisingly, it is possible to easily clean up the secondary thread using the bthread keys mechanism. So you can register a destructor that will run when the current thread is torn down, and so when the application thread exits, it can also cause the worker to exit. This was the second model that I implemented, and the first model turned out not to work so good with the NVIDIA driver. So the first model was a bit more naive. It spawned one worker for each active context, for context that was made current with GLX make current. And turns out it just regresses benchmarks, because when you try it with an NVIDIA driver, it activates some internal locking that I didn't want to investigate too much. But what I think happens is that NVIDIA driver wants to detect if it is running in a multi-threaded context. And if so, it wants to protect some of the internal data structures from concurrent modifications via GL API, and uses bthread mutexes to not do that. But it is not exactly clear what the actual logic implemented there is. And what is known is that you use the model above, and you arrange that the NVIDIA driver is loaded from the worker thread with DL open. Then it works as if it did not notice that the context is multi-threaded, which is great. For storing the function IDs and call arguments, I'm using a big ring buffer, a huge page, if I can get it. So when the application makes a GL call, the fake implementation just lays out the data in a natural way. So function ID, then arguments with natural alignment. And for arguments that are arrays, if they are below a certain size, I want to lay them out in line. So because the other choice is not to copy them and cause a synchronization, which is a not quite useful behavior. So threads needs to synchronize at least on 3 different occasions. So the consumer thread, the thread that performs calls into the real child driver, needs to suspend when the buffer is empty, so there is no work it can perform. The producer thread, so the thread that is originally an application thread, it needs to suspend when it is about to overflow a buffer, because you need it for correctness. And it needs to suspend when it wants to synchronize with the worker thread. So the mechanism here is to use just the minimal means to achieve that. So for 2 threads, have them maintain their pointers into the ring buffer, so the place the producer is going to write and the place the consumer is going to read. Have a Boolean flag for each of those, which is if the thread is suspended or not. And then suspend wake up can be implemented using just Linux fidexes, which is a good feed, I think. I do realize it is not a portable mechanism, but on the other hand, what I'm aiming here is highest possible efficiency, and it seems that going that way should be preferable. To generate the GL functions, there is a need to have automatic code generation. So the way to do that is to use some specifications. There are official specs, the old custom format, which is now deprecated. There are new specs which are XML-based. In addition to being XML, they are not expressive enough. They do not have some relevant information, for example, for GL texture parameter. It does not say that the array pointed to by the pointer argument is going to have length that is computed by function this and so. And this is what actually API trace can provide. Those specs are very nice. It is obvious that they are functional because, well, API trace works perfectly for tracing, and it is possible to use it for creating the for putting arguments in the ring buffer as well, because, well, it is almost the same thing. So from API trace specs, I go to a very similar representation that is just basically one more argument that shows the expected behavior of function can be async for functions that can be called asynchronously sync for functions like GL finish, GLX for buffers that need to synchronize. Naturally, there are other classes, and sometimes the behavior needs to be decided at runtime based on the arguments. From this representation, by applying the C99 preprocessor, I can go to 2 functions. The first function is supposed to face the application, so it looks just like a normal GL function, which stores the function ID into the ring buffer, then the first argument, then second argument, then it does some bookkeeping, and that's all. And the worker function, which is a internal function that is supposed to be called in a secondary thread, it does the reverse. It obtains the arguments and then it calls the real GL driver function at the very end. So naturally, all those are also preprocessor macros that expand to reasonably simple operations involving the pointer to the ring buffer.
So a bunch of those functions, if you go back to that slide, like this example, and if you're going to talk about this later, let me know. But like in this case, it seems like it would be better to just call GL vertex 2FV and give it the pointer to where X and Y are stored instead of pulling them off and putting them in registers and storing them somewhere else. And there's a bunch of examples like that in GL where there's kind of an explicit pass the separate parameters thing, and then also a pass a pointer to the parameters thing. And if you look at like how we generate GLX protocol for those, there's only one set of GLX protocol, and then in the server, it just uses the pointer version, and which is a real similar kind of setup like this, where you've got a client and server setup where one is marshalling the data and the other's unmarshalling it.
Good point. It is not easy for me to implement that because all of this is automatically generated, and at the moment I see no easy way to.
So in the XML that's in Mesa, there's a whole bunch of these functions that are decorated with a thing that's like vector equivalent, I think, where you'll have GL vertex 2F, and then somewhere in the XML for GL vertex 2F, there'll be a tag that's vector equiv GL vertex 2FV. So you know that they're equivalent. Just one of them takes a pointer to the pile of parameters, and the other takes the parameters separate. And like so, all the vertex functions, all the uniforms where there's like, you know, GL uniform 3F and GL uniform 3FV are decorated like that in our XML. And I did that for this exact kind of case.
Okay, thank you. So you're saying basically that there is no way for me to avoid XML in this working anyhow. Okay. Nice. The compiler translation for those functions produces this assembly. So even though the example is just a toy function, I want to show that the marshalling layer is extremely thin. So there are two instructions to get the context pointer, then one more indirection to get the ring buffer pointer. Then we just store an integer, which is the number of the GL vertex 2F in some internal array. Then advance the ring buffer, show the arguments in there, and make a tail call to a function that will make some final adjustments. It will store the ring buffer pointer back into the current data structure, because after that we are going to leave to the application, and we need to maintain the current pointer. And we also need to check if we are about to overflow the buffer, and if that is the case, we need to suspend. So basically just one more store and one more branch, and that's it. And the other side is even more simple, because it gets one argument, second argument, it adjusts the pointer in the register and jumps to the vendor libgl. So it is so simple because there is some abuse involved. So the first abuse is that I use a custom API that uses 3 registers for custom purposes. So the register that is usually used to return arguments for the return value is used to point into the vendor libgl, and it is loaded as in the same time as the address of the worker is decided. So the cost is a bit lower, and 2 registers to the ring buffer and the current data structure. And that is why advancing the ring buffer is just a register addition, nothing else. So the point here is all of this is done to make the Marshall and unmarshal layers as thin as possible, and the rest of the work happens exactly as it used to happen in vendor libjail. So, okay, so when that is done, there is a producer that shows the data into ring buffer, and from time to time it has to stall. And it is quite interesting to profile the stalls. And what happens, it can print out periodical statistics. So this is an example from Unigine Heaven. So it goes at 40 FPS. There is a lot of synchronizations per frame, but no buffer overflows per frame. Sync is the time that is spent in the producer thread waiting for the worker to catch up. So basically, this is the time we are going to hold up the application thread because we need something to happen from the GL side. And that 78% is further subdivided between GL export buffers, which has a high percentage, so we can guess that the benchmark is probably very GPU bound. But then there are some really odd things that shouldn't be there in an engine that wants to have high performance. There's GL get integer, check from buffer status, get error, and some things that we would like to not cause a synchronization. For example, map buffer range with an unsync flag that I will cover in the next slide. So looking at such a profile, naturally one wants to probably have some workarounds to make those synchronizations not happen. And there are some ways to do that. So for example, for GL get error and check frame buffer status, we can try to guess and maybe lie to the application, but if that is an opt-in feature and may happen to work correctly on some games, well, why not? It is so easy to do. A bit harder to do is to try and never lie to the application by tracking the actual GL state changes. And for example, so what needs to happen there for GL get integer is we need to track calls to GL bind buffer and use the value supplied there to answer GL get integer v queries that the application does. So what is potentially more interesting is the GL map buffer range with the sync flag. So there is a lot of expectation that this function should not cause a synchronization. And it was a huge contention point between Wine developers and NVIDIA developers. And so basically, Wine people said, hey, this shouldn't sync. NVIDIA said, this is not how our implementation works. But there is a way out. So what you can do is you can return an application, a malloc driver, a malloc buffer. So not a buffer that the driver would eventually map, but some unrelated thing, because it is write-only, it isn't synchronized, you can do that. So then you remember what you have given to the application, and when the application calls unmap or the flush function, you translate that to GL buffer subdata, and you free the buffer. Only if what you're going to subdata is going to be small enough, because if it is a multi-megabyte buffer update, you probably want to synchronize anyway, rather than copying megabytes of data in main memory. So with that in mind, we have a contradicting goals here. So on one hand, we want to have a very simple threaded dispatch layer, which for simplicity wants to perform a one-to-one mapping and have a lower overhead. On the other hand, for practical reasons, we want to avoid syncs. To do that, we need some hacks, and hacks come with a cost. So the approach I'm going to take is to separate it into two libraries. One library that will be called Tangle is the threaded dispatch library. Simple, correct, and fast, hopefully in that priority order, and should be good enough for applications that are tuned for threaded-like driver behavior. And then the horrible hacks can go to a Mangle library, which can do things like lying on shell get error, transforming my buffer to subdate, and so on. And it will be possible to just incrementally write hacks based on what some games or, well, basically games might need. So the last part of my talk is about things that I thought when writing this functionality about OpenGL. And the first thing is, in OpenGL, there is no way to enable the driver to access a memory range asynchronously. So what I want to do is quote it above. Basically, there should be a call that says the next texture upload or memory copy can happen asynchronously, because that is how the hardware wants to work. What game developers might want is they might want to map a resource file into memory and use that memory map to upload the texture. Then have a barrier just after the upload, do some unrelated things like shader compilation, things like that, and then wait for the upload to finish and unmap the resource file. So currently there is a problem because the second step is going to block. There is no way to jail the image from application memory asynchronously, but things shouldn't be like that. And this was done before. It is not new. There is a 98 SJX sync extension. There is an NVIDIA extension from 2002. NVIDIA has a similar in-spirit functionality in CUDA, because for compute, asynchronous copies are essential. So why doesn't OpenGL has this? Why doesn't OpenGL have this? The second potentially missing piece is callbacks on fence objects.
So back on the previous slide, there's two other extensions for doing that, and Mesa actually used to have one of them. There's the Apple client storage, which is the one that Mesa used to do. That's exactly your middle use case. It said, here's some of my memory. I'm going to do a text image from it, and you can hang on to my pointer for a while, and I'll try to figure out when the GL's done with it. And it was for exactly that kind of use case. But after having it in Mesa for years and exactly 0 applications using it, it was causing some, I don't know, there was some annoyances with the implementation of it, so we deleted it. And then there's also, more recently, the AMD pinned memory, which is kind of similar to this. It lets you take some malloc memory and say, give me a buffer object and use this region of memory as the backing storage for that buffer object. And so you kind of wrap a GL buffer object around something that you mallocked, and then you can do anything with it that you could do with a buffer object, like do PBO texture uploads. So it can also do this kind of stuff, but I don't know that AMD has seen very much uptake of that extension, and I think it has some other weird quirks about it too.
Okay, thank you. So the next potentially missing piece is callbacks on fence objects. So GL already has a concept of callbacks for debug output, and what I'd like to see is a callback for the point in time when the fence object created by GL fencing is fired. So why I'm interested in that is because in the threaded dispatch described here, the GL client wait sync function will need a complete sync, so it will not just flush the pipeline until the moment in time then the sync happened, but also it will wait for completion for all the recent API calls that the application submitted. And having a callback would help with that massively. And actually, fence objects are unusual because, for example, fencing is a function that conflates the creation of an object and the actual GPU operation. And it is really odd because, again, for threaded dispatch, I think it would be beneficial to have those separated. Because when creating a fence, you return a value to the application that it is going to use. But when the application wants to place a fence into the GL command stream, it doesn't need any value returned.
Aren't there GLX APIs that will enable you to create a synchronization object from a Windows system object? And if you did, then lying about client wait sync back to the main thread would be saying, yeah, I guarantee X11 has in fact passed this synchronization point, so now your X11 source operations would be able to see the bits that GL drew. So you would be defeating those, like those, if you were actually to shortcut client wait sync by saying, oh yeah, you are synchronized with this fence, carry on, then everything that your GL API wasn't wrapping would now be seeing an inconsistent state.
No, intention to lie about completion was never implied. So when the application calls client wait sync for a fence that happened for a fence that was placed eons ago, you want to sync until that fence, but not further. You do not want to wait until all recent texture uploads happen.
So why would the callback help?
Come again?
So why would a callback help you here? Why you're trying to eliminate part of this stall, right?
Right.
How would the callback help you?
The worker thread, the secondary thread, would register a callback. And in the callback, it would update a flag in memory and futex wait that flag. So when you futex wait that flag, the GL client wait sync, it can inspect the flag, and if it is not fired yet, it can futex wait on that flag, and the right thing will happen.
But that's equivalent to what GL client wait sync would do if you just synced through anyway. Either the fence is passed, in which case going into the GL will get you the answer, or it hasn't, and then you'd be stalling anyway.
Yes.
So this doesn't actually save you anything.
No. It does, because from the time when the fence was submitted, the application might have submitted some heavyweight work, like a texture upload. And you do not want that heavyweight work to catch up.
But that's not what client wait sync would do. You said client wait sync. You're saying I want to wait on this fence object, and then later I do some texture submission.
Yes.
He's trying to emulate the exact semantics of the GL here. The issue that I believe he's describing is that there may be more requests queued after, and with this whole producer-consumer queue that's part of Tangle.
Oh, because he's queued a bunch of stuff, so he'd have to wait for his own.
Right.
Oh, well, you don't need this then. All you need to do is track your own ring buffer and figure out what fences you've submitted.
Not that easy.
Sorry?
I have thought of that. I do not see an easy way to do that. So callbacks things seems like the best option, basically. But, well, my first time tinkering with the GL on that level, so sorry. Okay, so anyhow, again, four-letter word, CUDA, has the similar concept. It has an ability to register callbacks for compute fences. So obviously the ability to do that is there. Why not have it for GL sync? So basically, that is the main meat of my talk. If I have some time, I have some more really odd slides. But basically, if any questions, I will happy to answer. And thank you for the awesome XDC.
So quoting from the wiki, at present, a work-in-progress implementation can outperform NVIDIA's counterpart in Unigine Heaven. Do you have figures or something?
I was going to...
I asked you for a demo earlier. I know you don't have a demo, but you have figures.
Well, so I do not have the testing set up on my laptop, and I was trying to do that by SSH to my home, and I cannot reproduce it now. So what I basically need to do right now is to retrack that claim. But what I saw months ago is that on certain configurations, NVIDIA threaded GL can actually regress in Unigine Heaven. And this implementation can provide a speed up, but only if you are definitely not GPU bound. So it means a smaller resolution for Heaven, because otherwise it just goes slow either way.
Can you go way back to like slide 4? Way back. One more. Synchronization. Here we go. Someone else can ask a question. I'm trying to remember what this was. Go back. Okay, go back one. One more. There was one that said GLX on it. I'm trying to figure out where that was. It can't be second slide. 5th. 2, 3, 4, 5, 6, 7. Come on. I feel like a jerk now. There we go. All I'm trying to do is figure out a bug why this can't possibly work. So there's really no reason for us to wait for this. So it's fine. Forgive me.
Oh, no idea.
About the approach to clean up on this slide, I am not sure if it is entirely correct. What if an application starts rendering something in one thread, and then creates another thread, synchronizes it with the first thread, terminates the first thread, and continues in the second thread? Is this kind of usage allowed by the specs or not?
No, what basically, in the second thread, it will need to call glx make current. And when glx make current is called, I'm going to have the proper tracking. So it will work as intended.
Okay.
So
Don't worry, it's not another conference.